Hi again. As we discussed in the last video, when we are dealing with boundary layer problems, we can find simple scaling relationships such as the thickness of boundary layer should scale as kinematic viscosity nu multiplied to x over u0, the square root of the whole expression. But as we showed, the numerical prefactor for this expression is relatively hard to find because we need to solve this type of partial differential equation. You have seen the lecture videos how to turn it into a relatively simpler ordinary differential equation using similarity parameter and similarity equation. But even that ODE is not easy to solve. It's a nonlinear ODE. You need to solve it using numerical integration. And then you can find exact prefactors from that numerical integration or numerical solution. And that's what Blasius did. But as we discussed in previous lecture videos, there is also a more general and kind of integral approach towards this problem. Here we are dealing with differential equations, but you can also think about this problem in terms of integral of the identities that you have. And the integral approach is easier in terms of the mathematics involved. It's not exact, it's an approximate solution, but it's good enough to give you relatively accurate final answers. That's what we called von Karman-Polhausen method, and in this review we will just go through it relatively quick. We notice that the basic idea is based on both conservation of mass and momentum. If we think about conservation of mass, the fact that our velocity profile inside the boundary layer is not anymore uniform flow, and we are losing some of the momentum due to this velocity profile that gradually rises from 0 due to no slip boundary condition to u0 outside the boundary layer, will lead to two significant consequences. The first consequence is the fact that we lose some mass. So in order to conserve mass, if we follow the shape of a streamline which remains flat before reaching the flat plate, as the streamline reaches the flat plate, the mass that we have lost here should be compensated by a small displacement or the vertical shift of the streamline upward. Here I am drawing it with a green line in an exaggerated manner, but you remember that we can actually find exactly how much this streamline will be displaced vertically upward, and that's what we call displacement thickness, or delta star as a function of x, which is defined as integral from 0 to infinity of this expression, which is 1 minus Vx, which is varying with y, divided by u0, which is the velocity outside the boundary layer at the position x. And this whole thing is inside bracket, and the integration is happening with respect to y. So this is how we define displacement thickness. And if we elevate our streamlines by this amount upward, we actually satisfy conservation of mass. And that's what really happens. The streamlines, if you look at the demonstrations for boundary layer that you have seen in different videos, streamlines are slightly getting shifted upward, and they are getting shifted upward by small but still finite non-zero thickness, which is called displacement thickness. If you not think about a contour volume that is even corrected by this displacement thickness to satisfy conservation of mass, and you use conservation of momentum, you will notice that you will actually lose some momentum, and the lost momentum is captured by what we define as momentum thickness. And this is the idea that we introduced by the symbol theta of x. And theta of x is defined very much like displacement thickness is a definition as an integral from 0 to infinity of Vx, which is varying with y at a fixed position which has a uniform velocity u0 as a function of x outside the boundary layer, multiplied to bracket open 1 minus Vx divided by u0. And this integral is again with respect to y. That's the variable that we are integrating over from 0 to infinity. And we notice that this momentum thickness really tells us how much momentum we are losing per unit weight into the board once we multiply it by rho u0 squared. So rho u0 squared times theta of x is the amount of momentum, linear momentum, that we lose as we reach a position x on this flat plate. And that lost momentum happens mainly due to the fact that we have friction at the wall, and the wall shear stress, as we go further and further, gradually takes more and more momentum out of the flow. This was the point that we defined, or we introduced the idea that we can actually derive an interesting integral equation, which is called von Karman and Polhausen equation. So von Karman Polhausen momentum integral equation. And the expression is simply as described in the lectures, is the integral of x component of Navier-Stokes from at a fixed position x with respect to y. We integrate this equation from 0 to infinity, and we show that it can be rearranged and written in this manner that has a significant meaning. D over dx of bracket open u0 squared at position x multiplied to theta, which is momentum thickness at position x, that's our first term, plus the displacement thickness, which is delta star at position x, multiplied to u0 du0 over dx. And keep in mind that in a general flow, u0 indeed can change with x. In a flow over a flat plate, since the geometry is flat and there's no change in cross-sectional area, u0 from the outer flow, we see that u0 is not changing with x, so du0 over dx will be 0. But for a general shape, general profile, a curved profile or airfoil of a wing, for example, you may have variations of u0 along the airfoil. With x, u0 will vary. Du0 over dx will not be 0 anymore, and this term should be kept here. And these two terms are added together, and their net sum will be equal to the wall shear stress, tau w, that's the shear stress at the wall at position x, divided by density, which is rho. This expression has a significant physical meaning, and what it really means is the fact that you are losing momentum because of the action of wall shear stress. The rate at which you are losing momentum is equal to the value of wall shear stress at position x. But it's not the only term that is important in the balance of linear momentum in the x direction. If you have a pressure gradient from outside flow, the pressure gradient that the outside flow is imposing also inside the boundary layer, if that pressure gradient is present, you will have also certain net force in the x direction because of the variations of pressure with respect to x, and that is captured through this middle term by the use of Bernoulli equation. So if you go to the derivation of von Karman-Polhausen equation, this second term comes from the simplification we did for dp over dx term from use of Bernoulli principle for the outer flow. This von Karman-Polhausen momentum equation is exact, but what we will do is usually we take the compensation in approximating a certain mathematical function that describes the velocity field inside the boundary layer. A polynomial is a good example, for example. We satisfy certain boundary conditions to find the constants of that polynomial, and once we have the velocity field, we can construct the momentum thickness and displacement thickness based on the profile that we have chosen, and everything will be a function of, for example, the thickness of boundary layer delta, which is varying as a function of x. And then we put all this information inside this equation. The only assumption or approximation we have done is a certain velocity profile that we replace in Vx as a function of y here. When we put them in von Karman-Polhausen equation, everything simplifies to a relatively easy and a straightforward ordinary differential equation for the thickness of boundary layer delta as a function of x. And our main goal would be to solve that and find what would be the solution of delta as a function of x. If we find and we solve that, usually we get the form that we described here, but the nice thing would be that it also allows us to calculate the numerical prefactor, and the better is the approximation for velocity field that initially we have used in our approximate solution, the more accurate would be the prefactor that we get after our calculations are finished. And this method, I really suggest you guys to go through it and at least try it for a few examples that we have posted in your problem sets. You can be sure that in the exam we cannot ask you to do numerical integration and do things as complex as Blasius solution has in itself. But we can easily give you a certain problem and suggest the right approximate profile for the velocity and ask you to do different steps of the von Karman-Polhausen approximation method in order to find a reasonably accurate form of the boundary layer thickness in a problem. Once the boundary layer thickness has been found, you can find things like wall shear stress distribution along X. You can find the skin friction that is acting on your geometry. And all the other unknowns that are of interest in your problem can be found and resolved, or basically their mystery will be resolved and their expressions would be found easily by the output of delta as a function of X.